The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're looking up to the skies and into the past, exploring the history and technology of astronomy and astrophysics. Later on in the show, I'll sit down with Chris Beckett, and we'll talk about the whys, wheres, and whats of modern amateur astronomy. But first, let's go back in time with author and physics professor Alan Hirshfeld. Hello and welcome to Science for the People. I'm Rochelle Saunders. I'm here with Alan Hirshfeld, professor of physics at the University of Massachusetts Dartmouth and an associate of the Harvard College Observatory. He lectures widely about science history and discovery and is a frequent contributor to the Wall Street Journal, Sky and Telescope, the American Journal of Physics, BBC History Magazine, and American Scientist. He is the author of several books, including Parallax, The Race to Measure the Cosmos, The Electric Life of Michael Faraday, and Eureka Man, The Life and Legacy of Archimedes, among others. He's here today to talk about his new book, Starlight Detectives, How Astronomers, Inventors, and Eccentrics Discovered the Modern Universe. Welcome to the show, Alan.
Thank you, Rochelle.
So this book really focuses on the advancement of technology in the field of astronomy and the discoveries that advancement led to. What motivated you to write on that theme?
Well, everybody knows the story of Galileo and the telescope, how he took this newfangled instrument in the early 1600s, pointed it to the heavens, and just discovered new vistas in the cosmos that had never before been seen during the entire course of human civilization. And I came to learn that there was a comparable period in the late 1800s when technology came to the fore, augmented the telescope, and likewise opened up these new vistas that had not been seen before. These technologies were photography and spectroscopy. And I felt that this period, which I just became fascinated with, really hasn't gotten enough press, enough play in books, and so I decided to explore it myself.
So take us back to the era of classical astronomy. How was this era different from the astrophysical science practiced today?
Yeah, very, very different. I mean, if you look at the headlines today, modern astronomy is extraordinary by every measure. But it did require astronomy to go through a dramatic transformation during the late 1800s. So before, say, 1850, before the introduction of photography and spectroscopy to astronomy, to astronomical observation, all that astronomers could do was apply their eye to the eyepiece of a telescope and inspect whatever was out there. And the emphasis in astronomy at that time was on the positions and the movements of stars, planets, the occasional asteroid. The meaning of these points or clouds of light was entirely unknown because the physics hadn't yet been developed. So it was a very, very tedious mathematical kind of process of cataloging without really knowing what you were looking at.
How much was the early classical astronomy driven by the needs of transoceanic navigation?
Well, in the 1700s, certainly getting into the 1800s, it became necessary to pinpoint one's location, say on an ocean or in the middle of a continent, with greater precision. When there were shipping lanes that were passing close to dangerous coastlines, when there were regularly scheduled railroad trips, it became essential to know the time, the location of the various moving pieces of commerce. And the best way to do it at the time was through astronomy, through celestial navigation, not necessarily standing out and sighting the stars by eye, but through very, very careful measurement at observatories around the world of the locations of particular stars or configurations of Jupiter's moons, even the passage of the moon's phases. To time these very, very precisely gave astronomers a real sense of sort of a global positioning system all around the globe. So it was in the national interest to fund observatories to go out and very, very carefully measure where stars are, where planets are in the sky. And likewise, once you have these cataloged, this tremendous number of stars, thousands upon thousands of stars, once their positions are fixed and their gradual movements are also determined, you have the basis then to tell when a new star might pop up, or a star that has been shining for a very long time might change its brightness or perhaps even disappear. It was crucial to really lay out this grid of the stars on the sky to great, great precision.
Well, how are the challenges of classical astronomers different from today's astrophysics? I mean, I feel like the job descriptions are so different, so there must be different challenges there.
Yeah, as I said, there was a dramatic transformation in the late 1800s of what astronomy meant and what astronomers do, the very reason for being of astronomers. Before this transition, the emphasis was on very, very precise position measurement. This did not necessitate the building of big telescopes. It required the building of small but extremely stable, extremely precise telescopes. It required repeated observations of, say, the passage of a star over the meridian, over the north-south midpoint of the night sky, which would determine the position of the star. And then a very, very careful, again tedious mathematical reduction of all of these timings, these position measurements, to make sure that all of the measurements made by all of the observatories all over the world cohere to a common system. So it was really a sort of a practical mathematics that was being done, a measurement-based mathematics that was being done. When there were the first inklings of what we would call astrophysics, when photography started to be used in some observatories, and some astronomers attempted to measure or detect spectra of stars. That was considered at first something of a soft science. It was not really quantitative yet. So for many, many decades, the early astrophysicists were really considered second-rate astronomers compared to the precision astronomy that had been carried out for centuries by professional astronomers. Now, fast forward into the early 1900s, certainly up to today, and the precision requirements of today's astrophysical observationalists are just as severe, just as stringent as their old-time brethren who are measuring just the positions and movements of stars.
You're listening to Science for the People, and we're talking with Professor Alan Hirshfeld, professor of physics at the University of Massachusetts Dartmouth, about his new book, Starlight Detectives: How Astronomers, Inventors, and Eccentrics Discovered the Modern Universe. I want to talk a little bit about William Parsons, the Earl of Rosse, is it?
Yes.
And his Leviathan of Parsonstown. Was this the first really big telescope?
It was not the first really big telescope. I guess it depends on your definition of really big, but I would say really big would have come in the late 1700s with the famous astronomer William Herschel. Herschel built many, many telescopes. His two biggest, one had a mirror, a reflector telescope of 19 inches in diameter, but based on his success with that, he actually introduced a telescope whose mirror was 48 inches, a full 4 feet across. That latter instrument didn't work very well, But that would be recognized as the first, I don't know what you'd call it, a mega reflector, I guess. Lord Rosse was certainly inspired by Herschel's example and spent quite literally a decade of experimentation to gradually increase the size of his own metal reflector telescopes until he achieved in 1845 a complete instrument that was 72 inches across, full 6 feet across, which he then placed on his estate in Ireland.
How much of a move forward was the Leviathan? How improved was the view from what was typical at the time?
Well, astronomy at that time, in the 1840s, was divided into two camps, as I've already alluded to. There were your professionals who were measuring positions and movements of stars, planets, comets, and such, who worked with rather small telescopes, mostly lens-based refractor telescopes, whose apertures were in the inches, 6 inches, 9 inches at the extreme. But then there was this other group, and these were mostly amateur astronomers, who adopted reflectors, who made them larger and larger, and there the extreme, again, is Lord Rosse's 6-foot diameter reflector. These astronomers were interested in pushing the envelope, so to speak, to peer deeper into space, far beyond the solar system, to explore some of those regions that in small telescopes just appear to be void of stars and nebulae. And that's really what those astronomers were doing. This was such an experimental kind of thing that the professionals did not eagerly jump into that arena, to deep sky astronomy. Their advancement was really keyed to their performance measuring star positions and reducing star positions and publishing catalogs of star positions, maybe the occasional comet discovery, determination of a comet's path, say, and in a couple of cases, discovery of another planet.
It's interesting. Things seemed a lot more sort of hands-on back then. The same people who used the telescopes often also built and created them. You really had to be an astronomer and a bit of an engineer back in that day.
Well, certainly for these newfangled reflector telescopes that were being introduced. Now, the reflector telescope, a telescope that collects celestial light on a mirror, which then focuses the light through an eyepiece, that had been around since the days of Isaac Newton in the late 1600s. So it was not new. The newness came from the increase in aperture of these telescopes. There are all sorts of practical problems that arise when you take a mirror made of solid metal at the time and you just scale it up to many feet in diameter. It will weigh many tons. And so you have the practical problems of how do you support such a mirror? How do you point it to different places in the sky so you can view different celestial objects? How do you allow it to come into temperature equilibrium with its surroundings at night? So it is true that there were so many problems, practical problems that were involved with these mammoth early reflector telescopes that you needed to be a true engineer, a craftsman, a tinkerer, an inventor. They were considered very, very problematic instruments and were not trusted by and large. Lord Rosse, as I said, spent about a decade's time just experimenting with the means to make such large mirrors and figuring out how do you mount such a mirror? What might a telescope tube be made of? How do you support it? How do you move it? All of these kinds of things. And I can't say that that telescope was dramatically productive, except in one sense, one discovery that it made. And that was its increased aperture allowed it to see some objects that had eluded the very, very small telescopes. The night sky is filled with these faint little whirls of light called nebulae. Maybe the most famous is the Orion Nebula, which is a gas cloud below the belt stars of Orion. There's also the Andromeda Nebula. So these faint hazy patches in the night sky were entirely mysterious. But what Ross found with his enlarged telescope was that some of them had a very peculiar, distinctive spiral form, like pinwheels of light. So in the few years that his telescope was operating profitably, that was the one major discovery. That sort of kicks off, in a sense, my book. In the beginning, there are these mysterious spiral nebulae. Nobody knew what they were, but they quickly found a couple of dozen of them. And by the end of my book, everybody knows what the spiral nebulae are and believes that there are thousands, literally millions of them scattered all over the sky. So this is the kind of transformation that I cover in my book. And a lot certainly had to happen in between for that tremendous advancement in understanding about these particular objects and the universe itself.
It's interesting how much of some of the technological advancement was, as you said, done by amateurs. And in a lot of cases, they were funded entirely with their own money. And even sometimes, these giant telescopes would be bolted onto their homes. You don't really see that anymore.
Yeah, without a doubt. I mean, if you wanted to be a serious amateur astronomer at that time in the 19th century, you had to have money. You had to be wealthy. In the case of William Herschel in the 1700s, he had a day job as an orchestra conductor and music teacher. His discovery of the planet Uranus allowed him to get a stipend from the king, and that's how he supports himself. But the people who I write about in the latter half of the 1800s, each of these was an amateur astronomer who made his wealth, made his fortune in some kind of business or through inheritance or through marriage, and then put that money toward a very, very serious venture into observational astronomy. Nowadays, the successors, the amateur astronomers these days, it's quite amazing the level of technology that they can bring to bear in their nighttime observations. Telescopes now, while still relatively expensive, or you can get a very good telescope for the same price as a widescreen TV, but you can equip it with electronic cameras, even spectroscopes, very, very sophisticated kinds of equipment. You can control these telescopes with computers. It's a remarkable renaissance in terms of amateur involvement in serious research level astronomy.
So you spend a lot of time talking about the camera and how it was used to advance astronomy. How much of an impact did camera technology have on the field?
Well, in the beginning, none at all, virtually. Photography was invented, the exact date is sort of hard to pinpoint, but there were a couple of people who were working in photography as early as the 1820s, if not before. The key advancement was not so much to produce an image on a chemically sensitive surface, but to figure out the chemistry of preserving that image so it didn't disappear as you were looking at it. By the late 1830s, the daguerreotype had been perfected. There was also a similar technology in England that had been perfected, the Talbotype. So the photography had been kicking around for a while, but was formally announced to the world in 1839. So you'll remember that Lord Rosse's big telescope was built in 1845. So we had both the building of big telescopes and the introduction of photography almost simultaneously in this timeline in the advancement of astronomical observation. But photography in its earliest incarnations was extremely, extremely crude, troublesome, noxious. And, from the perspective of a professional astronomer whose salary was being paid by an institution who was merely interested in star positions and celestial navigation and such, to spend time experimenting with this fledgling technology, which today just seems so obvious could advance astronomy, back then it was truly believed that nothing would surpass the human eye in terms of acuity through a telescope. So cameras were very, very experimental, a serious hobbyist kind of endeavor. And it remained that way for several decades before the photochemical technology really advanced to the point where a camera attached to a telescope could exceed the sensitivity of the human eye. It could actually become an instrument of discovery. When in the 1890s, a comet was discovered on a photograph, and then nearly simultaneously an asteroid was discovered on a photograph, and nearly simultaneously binary stars of a particular kind called spectroscopic binaries were captured in the photographic spectrum of what appeared to be a single star but was actually a dual star. Astronomers began to sit up and take notice, and then gradually and then quickly got into the business of celestial photography. So the turning point really came in the 1890s.
Just so our audience really understands what we're talking about when we say adding photography or adding a camera to a telescope. I mean, cameras today are ubiquitous. Everyone's got one on their phone. But the cameras of that era were not point and click. These were sort of cumbersome processes. Can you walk us through some of those early processes?
I mean, camera literally means room or box or something like that. You had a box that was bolted on to the back of a telescope, and in the back of the box there was a glass plate or a metal plate on which were photosensitive chemicals. And the idea, just to put it simply, is to point your telescope at, let's say, the moon, and let the light of the moon pass through the telescope, and instead of into your eye, onto this photosensitive plate. Now, the photosensitivity early on in the 1840s and 1850s was so low that even getting a picture of the moon was a challenge. And stare at the full moon some night, and you can sort of gauge how bright it really is. Even so, it would take a very, very long exposure to show anything of the moon on a photographic plate back then. So the astronomer had to prepare the plates, mix the chemicals, deal with all the noxious fumes, such as mercury, for example, was used in the daguerreotype process. It was not a very helpful thing to do. It was messy. You were in the nighttime observatory. Things could spill. You could trip. You could drop your glass or metal plate. It was really, really a problematic kind of observational list of things to do compared to just putting an eyepiece in there and looking through the telescope. So it was a tremendous challenge to obtain a photograph, and then it was similarly you had to go into the darkroom and develop this photograph, look at it, realize that maybe you didn't expose it long enough, or that the telescope had been bumped along the way and the image was blurred. It was an extremely frustrating experience for any astronomer. And when you read about what they went through, you just get a sense of the passion that was involved in carrying out these early experiments on celestial photography. And I try to convey through the ground level view of an observatory in the 1850s or 1860s what someone might have experienced. I hope that when readers read accounts of astronomers like Andrew Common or Walter de la Rue, that they'll really feel a little chill in their bones from the night air of the observatory, just seeing that they spent hour after hour after hour trying to obtain a passable photograph of the moon or of the Orion Nebula, let's say.
Some of these guys were really quite remarkable. You just sort of think about the skill sets we've already talked about that you had to have. You had to be a bit of an engineer. You had to have financial stability. You had to, I'm assuming, to be of value, you had to have a mathematical background so you could start calculating positions and things like that. You had to be a chemist if you wanted to start using photography. You had to be willing to, sit outside and be really patient, and cold nights all night long. These guys are really dedicated.
They are certainly dedicated. As you hinted there, I mean, the boundaries among the different disciplines of astronomy, chemistry, mathematics, physics were not so firmly set as they are today. You had to be an interdisciplinary kind of investigator. The energy that these people brought to this endeavor, I see today when I gather with my amateur astronomer friends. Every time our university has an open house at our observatory, the local amateur astronomy society, they come with their telescopes. They set up the telescopes on the lawn. We could be talking about middle of February, a freezing night out there, and they come and they show people images of the heavens through their telescopes. They are so dedicated that their behavior, their commitment really resonates with me when I'm writing about these astronomers of the 1800s. I see the same sort of dedication. And it's really a profound feeling to see this sort of human thread of dedication and passion toward exploring the universe just continue uninterrupted. And I think that's probably the way it has always been, since there have been astronomers, sky watchers. There's just something that appeals to some people about what is out there in the dark, what is above our heads out in space.
So before we started trying to integrate cameras with telescopes, how did people record what they saw?
Well, you basically had two choices. One is to write about it. I saw, so-and-so on this night in that position. Or you describe what you saw on the surface of the moon, for example. And you're limited to your own vocabulary or poetic expressiveness. The alternative, if you had any talent at sketching things, well, then you sketch. You look into the eyepiece, glance into the eyepiece, then go to your paper with your pencil and you start penciling in the best representation that you can make of what is seen through the eyepiece. Now, this, of course, is problematic in that probably few astronomers of the day were skilled illustrators. So there were actually observatory artists, observatory illustrators, whose job it was to look through the eyepiece and sketch, draw pictures of what was seen there. Some of these pictures are quite extraordinary, not so much in their faithfulness to what the object really looks like, but just as works of art. It was very hard, obviously, for an astronomical illustrator to hold back and not sort of convey more drama in an image than there really is presented to the eye. If you look at a nebula through the eyepiece of a telescope, it's typically very, very faint, vague, maybe at the limit of vision. You don't want to draw, as an astronomical illustrator, just a little smudge on a piece of paper, but you want to fill in what you think might be there, what you think you are seeing. And so that's the general sense of what you get when you look at old-time illustrations of, say, the Orion Nebula or Jupiter or such, or even the moon's surface. There's a little bit more there than really should be there from the perspective of an experienced astronomer who knows what they look like through the eyepiece. And that was one of the tremendous attractions of photography, its objectivity. As astronomers used to say, the star impressed itself upon the photographic plate. There was no intermediary to interpret the starlight. So the objectivity and the permanence of photography was one of the early appeals. And if you look at some of these old photographs, they are terrible. They're really awful from a modern perspective. And yet there was something in them that appealed to astronomers because they had a sense that this is what a celestial object really looks like. As it happened, the eye has a somewhat different color sensitivity than the early photographic emulsions. So there should be no surprise that some of the illustrations versus some of the early photographs actually look somewhat different from one another. The camera and the human eye were actually seeing something different when they were looking, say, at the Orion Nebula.
One of the other complications in trying to take pictures of the stars is that the stars are not static in our sky. They're constantly moving. And I guess with the long exposure times of some of that early photography, I'm guessing that would have been a bit of a problem.
Yeah, more than a bit of a problem. It was a major problem, if not the major problem. So independent of the improvement in chemical emulsions, as you said, the night sky objects appear to move from horizon to horizon, a reflection, of course, of the Earth's rotation. But this means if you point a telescope at an object in the sky and your telescope is stationary, the object will appear to just creep across the field of view and eventually out of the field of view. Now the eye can follow that, but a camera, if the telescope is stationary and you take a picture, a time exposure picture of a star, what you're going to wind up with is a streak of light across your photographic plate. It was essential for astronomers to move the telescope and the camera to track the celestial object that they were photographing and to track it extremely precisely. And the less precise, the more blurry your image. And so a great deal of effort was expended improving the mountings of telescopes and the motors or the gravity gear drives that drove these telescopes. It doesn't seem like it'd be such a complicated affair, but the requirements were very, very stringent. In order to get a sharp, high magnification image impressed on a photographic plate, you would have to expose the plate for maybe an hour's time, and during that hour's time, the telescope had to track precisely on the celestial object without deviation. This was an extreme, extreme challenge that took literally decades to solve, but was pretty much solved by the end of the 1800s just through mechanical innovation.
This is Science for the People, and we'll be right back to talk more about the history of astronomy and technology after this.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Rochelle Saunders. I'm here with Professor Alan Hirshfeld. So both telescopes and photography will continue to improve, and the next major disruptive technology in the field of astronomy seems to be spectroscopy. What is it, and how did we get it?
Yeah, spectroscopy was the equal of the introduction of the telescope itself. It was an extraordinary innovation, both in the laboratory and in the observatory. So when you just look at any object, look at a star, let's say, with your eye, all of the different wavelengths of light that are emitted by the star are all jumbled together. They strike your retina in unison and you see just an image of the star. What a spectroscope does is spread out the star's light in order of color, or the technical term would be wavelength, so that you create a rainbow of colors, all sorted out. Now, this is certainly a very beautiful thing when you see it in the sky, a rainbow, but it can be a very useful, groundbreaking kind of technology when used in science. The story of the introduction of spectroscopy is just fascinating, and there are just incredible individuals involved in bringing spectroscopy to bear on science. It's one of my favorite groups of scientists, a duo called Bunsen and Kirchhoff. We've heard of Bunsen, of the Bunsen burner. Gustav Kirchhoff was a very famous physicist. But the two of them, who are very different in their manner, style, one was a chemist, one was a physicist, they became fast friends, and together they were able to make the spectroscope a practical device in the laboratory and very, very quickly in the observatory. So what happens in the observatory, if you sight a star, you pass its light through a narrow slit, you pass that light through a prism or its equivalent called a diffraction grating. You spread out the star's light in order of wavelength, and strewn through this rainbow of colors, if you look very, very carefully, you'll find absences of colors, spectral lines, we call them. And this was first seen in the early 1800s. It was studied by the instrument maker Fraunhofer. They're called Fraunhofer lines now. What Kirchhoff and Bunsen were able to show is the patterns of these dark spectral lines in the rainbow spectrum of a star actually match up with the pattern of bright spectral lines that is given off by a substance that is glowing in a laboratory, and that each chemical element that exists has a unique spectral line pattern. And from this, they realized very soon, 1859, same year that Darwin's Origin of the Species came out, Kirchhoff and Bunsen realized that you could actually do a sort of laboratory analysis of the sun or of a star merely by passing its light through a spectroscope and identifying the patterns of its spectral lines. It was just a tremendous, tremendous advancement in the ability of astronomers to learn about the universe.
It sounds like spectroscopy was a pretty disruptive technology in the field. What changes did it bring to the field and sort of the culture of astronomers?
Well, in a sense, it validated the work that the early astrophysicists were doing. The idea that you could examine a star as though you were taking a scoop of the star's atmosphere, bringing it into a laboratory and subjecting it to chemical analysis. This made a big, big impact on the entire astronomical field. It took a while to perfect these techniques. I mean, as we already alluded to, if you're going to take a time exposure photograph of a star, your telescope is going to have to track that star very, very accurately. Now, if you're going to take the light of that star and spread it out into a spectrum, making it even fainter, you're going to have to track that star with your telescope for an even longer period. So there were a couple of decades of development before spectroscopy was really an integral part of astronomy. Again, that happened in the 1890s or so. But once photography and spectroscopy were both adopted by the professional astronomy community, things really moved quickly, and the entire field just changed. It transformed. And it was realized that an astronomer really had to be a physicist as well, and a mathematician as well. And there were efforts to really professionalize the field, to draw a distinction between the backyard amateur astronomers, so to speak, and the professional astronomers who were university trained. And it created quite a bit of upheaval in the 1890s between the amateur and professional communities. And even within the professional astronomy community, you had the classical astronomers, the positional astronomers of yore, versus their new counterparts who were using these new technologies. So it was a tumultuous time, the 1890s, but eventually settled in the early 1900s with a division of labor, you might say, and an appreciation of the various abilities of astronomers that are recognizably modern. The astronomer, the astrophysicist, they merged. They became the same. An astronomer was an astrophysicist and vice versa. And the amateurs who had spent decades innovating these fields, introducing them to the observatory, perfecting them, they were more or less, rudely left behind. They didn't have the mathematical skill, the academic training to really compete anymore with the professional astronomers, nor did they have the money to build the kinds of telescopes that really were called for starting in the early 1900s. Multi-million-dollar telescopes of great aperture that would be situated on mountaintops. So astronomy then became more of an institutional science as opposed to some backyard hobby.
So we're almost out of time, but I'm curious, how many discoveries or contributions to the field do amateur astronomers make today?
Well, today, again, I mentioned the fact that their technology is quite advanced and can make a backyard telescope into a decent research instrument. I was just reading literally yesterday in a magazine about amateur astronomers who had explored the variable stars in another galaxy. So this is the kind of breakthrough that was carried out in the 1920s with a telescope 100 inches in diameter. So these amateur astronomers of today were doing the same sort of thing with a telescope of maybe a dozen inches in diameter, but fortified with an electronic camera and with computer reduction. It's quite amazing what they can do. Comets are still discovered by amateur astronomers. Asteroids, likewise, are discovered and tracked by amateur astronomers. I started as an amateur astronomer, and I can tell you, the reward, even after decades of looking at the night sky through a telescope, it's still there. It's just mind-numbing to look through a telescope and see the Orion Nebula or see the Andromeda galaxy and know what it is and now what its history was.
Alan, thanks very much for being here.
Oh, you're welcome.
If you want to learn more about Alan Hirshfeld, his new book, Starlight Detectives, How Astronomers, Inventors, and Eccentrics Discovered the Modern Universe, or any of his other books, we've got the links to get you started available on our website at scienceforthepeople.ca.
On the next episode of Science for the People, we're revisiting an episode looking back in history and to the modern day to discuss women who defend and advance science and learning. We'll speak to author Faith Justice about her book, Hypatia, Her Life and Times, which examines the literary myths and primary sources on the life of the famous philosopher. And we're joined by Professor Zara Hazari to discuss her work on gender issues in science education. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm here with Chris Beckett, who has been stargazing since early childhood and involved in the Royal Astronomical Society of Canada for almost 2 decades. He is currently the president of Regina Centre, the national observing chair for the entire organization, and a partner of Grasslands National Park Dark Sky Preserve. Chris now lives in Regina, Saskatchewan, where he has taught 8 astronomy and stargazing classes at the University of Regina and helped coordinate hundreds of events during this time. He is currently studying how public policy can improve astronomy outreach as part of his master's degree. Welcome to the show, Chris.
Yeah, thank you very much, Rochelle.
Okay, so maybe let's start by talking a little bit about the Royal Astronomical Society of Canada. When did it start and what does it do?
Yeah, so the Royal Astronomical Society of Canada, it's a long name, but we just call it the RASC for short. It goes back to about 1868. We got our royal charter in around 1910. But right now we have over 4,000 members. And essentially what we do is we do public outreach in astronomy. So it's a really good tie-in with your program.
So how long have you personally been looking up at the stars?
I've been looking up at the stars since I was a very small child and looking up at the stars just through the window of our home. But my mother really fostered the interest, and she used to take me out to look at meteor showers and lunar eclipses and all kinds of great events going on in the night sky.
When did you sort of seriously get into it and start thinking, maybe I wouldn't want to do this a little more seriously?
Yeah, I guess it was about 20 years ago, and somebody bought me a book and a pair of binoculars, and then eventually I got involved in the RASC and started sort of working on their programs and the various things with that organization.
Is there an average age of avid astronomers? What age do people generally get hooked in?
Yeah, it's sort of a strange thing because many people really don't get involved until they're later in life. It's pretty common for people to be interested during their youth, but actually not really undertake it as a hobby until sometimes when they retire or even beyond. But there's been a lot of people that have done that and become incredible amateur astronomers, many of my friends included.
So what got you interested in the Royal Astronomical Society in the first place? I mean, why not just keep up with the backyard stargazing?
Yeah, well, that's a really good question. That's how I began. So I seriously get interested, started using binoculars and read a lot. And then eventually I kind of found that I sort of had reached that limit of what I could learn myself and wanted to find other amateur astronomers, get together with them and find out where they go and go to better, darker places to actually look at the stars and to learn from those folks. And it's a great organization for doing that.
It seems like it's an organization where there are so many different levels of involvement, both participation-wise and ability-wise.
Yeah, but most of our members, and we have about 4,000 or so, most of our members, they're really just describing themselves as intermediate amateur astronomers, but they have a wide variety of interests from solar observing to counting meteors. Some people do real contributions to science, like they watch variable stars or work on star clusters, which is something I've done, which is really great.
So you mentioned the term amateur astronomer. What does that mean?
Amateur astronomer, it's a term that essentially is based in the French language for amour, which is love, and that just means that we do it because we love it. We don't do it to get paid for it. We do everything we do in the RASC as a free public service.
Now, back in the old days, I know amateur astronomers used to discover almost as much as some of the professionals working in the field. How do amateurs fare on the discovery side of astronomical objects these days?
They actually fare quite well. I mean, it used to be that most comets were discovered by amateurs, and that still happens with David Levy, and even Vance Petru here in Regina discovered one. But now primarily they're discovering things like asteroids, and they watch variable stars, and even some amateurs are starting to detect exosolar planets and that sort of thing. They're involved in that kind of research.
So astronomy really is a field where if you're interested in some kind of civilian science, seems like a great way to get involved.
Yeah, it's pretty amazing. So one time I had a question about a star cluster. I was just looking at it through my binoculars. So I wrote the leading astrophysicist down in Penn State about it, and they had a lot of questions that only I could answer, and they, of course, had the answers I was looking for, and we ended up actually collaborating on some work, and they went and presented it with my images to the International Astronomical Union. So sort of like an accidental scientist in a way.
So what kind of events does the Royal Astronomical Society run?
Yeah, we run public observing events and public presentations. So what we do is in each of our centers, we have 29 astronomy centers across Canada. If you just Google it, you'll find them. But we have public speakers that come in. We just had somebody in from the Hubble Space Telescope Institute here in Regina, and we opened it up to the public, had about 30 members of the public show up, plus our members, and a great event talking about the Hubble Space Telescope. We also do public observing nights, so people set up their telescopes and invite the public to come out and look through them.
So I want to talk a little bit about actually going out and doing astronomy and stargazing. So maybe let's start with, what are some of the best places to stargaze in Canada?
So the best places to go are really the dark sky preserves, and these are locations that have been created specifically for stargazing and nocturnal creatures of the night of all sorts.
Can you talk a little bit more about the Dark Sky Preserve? Maybe give us some examples of ones that are around and what kinds of efforts are going into keeping them dark?
So we declare them as the Royal Astronomical Society of Canada, and what we do is we work with the groups, whoever are trying to declare the Dark Sky Preserve. For example, Parks Canada has been a wonderful partner for these type of locations. And what we do is we work with staff and we make sure that there's either no or very limited lighting. And then what we do is we coordinate with them to run events at these locations and to make sure that it's well publicized, that people can go there. So, for example, I work very closely with the Grasslands National Park. We put on at least 2 or 3 events in the grasslands every year and invite the public to come out and participate with us, look through our telescopes. But what makes these places so special is how amazingly dark they are. They're just, like when people think of a dark, starry night, they think of the Milky Way overhead just as a giant path, a giant set of clouds that are just streaming overhead to the horizon. And you really can see that in these places. And unfortunately, that's just not something everybody can do anymore, especially from our brightly lit cities.
When we're talking about Dark Sky Preserve, are there any enforcements that go along with the designation to try and keep these places dark?
Nothing too strict. We really try to leave it up to our partners, and to be honest, we've never really had any problems. If we do notice that there are some lights, usually if we talk to them, they're more than happy to work with us to help filter them, or to turn. I mean, we've even had the National Park System take out lights if they put in lights that didn't comply. So they're very happy and willing, and often it's just that they don't understand maybe that light wasn't a good light or something like that. But no, we've never really had to do any sort of enforcement or anything like that. Whenever people buy into this, they really understand what they're getting into with us.
I also saw mention of something called an urban star park on your guys' website. Can you talk a little bit about that?
Yeah, so urban star parks are something relatively new. I think we've got a few at East. There's one in New Brunswick, which is probably the one you were looking at. And what they do is they allow for a sort of a brighter lit cityscape area where there's a local buffer, and that buffer prevents light spillage into that area. So it's still somewhat lit by the city lights, but indirectly, so there's no local lights. So these are great spots for us to actually do outreach and public education and get people interested in stargazing and astronomy.
So these are sort of patches of dark in the middle of cities.
Yeah, and I really like the idea. I would love to get one here in Regina. It would be just wonderful. And there's all kinds of places you could do them in any city. Just, a local park, maybe there's a couple lights, and to work with the municipality to get them filtered or dimmed or taken out entirely.
Okay, let's say I want to start out as an amateur astronomer. Where do I start? What's the first step?
Yeah, the very first step is just to start going out and noticing the night sky. And we recommend to start reading some magazines. Sky News magazine is a Canadian magazine, and it's just excellent. Sky and Telescope is another one you might see on the newsstands as well. And we also tell people to make sure they use like a red filtered flashlight, and they're super easy to make. You just go to Canadian Tire, buy an LED light, put some red duct tape over it. So then what you can do is go out under the night sky and use that red light to actually read your star charts. That's the key, is actually to be able to learn and read the charts. A great book for people to get is called Night Watch by Terence Dickinson. And honestly, that book has everything in it that you need to start learning the night sky. It's just a wonderful text.
I suppose it would also help to find the dark sky nearest you.
Yeah, it can help, but I've been really surprised at what people have been able to do just from their driveway or from their window. In my class, I had an individual, and she was doing all her astronomy from her living room window because she just couldn't go out at night anymore, but she was still able to see a large section of the sky. And so that really inspired me to encourage people to just try it. Like whatever they have, even if they have a brightly lit yard, and they're able to get out there, or an alleyway or a fire escape. I have a friend, he's observed thousands of deep sky objects from his balcony in a city down in Halifax. So you really can do it anywhere you are.
What about equipment? Or what am I looking at for actually things I need to buy to get started?
The very first thing is to realize that equipment isn't central to doing astronomy. It's actually learning those constellations and the patterns in the sky and starting to understand how the sky moves and works. That is essentially the most important thing people can do, because the telescopes and binoculars that are readily available now very cheaply, they all work quite well. So I never make any one recommendation. If people are interested to get some of that equipment, I say, hey, go for it. And then make sure you learn those stars and constellations. They're just so important, and that's really what will keep your interest and keep you looking up in the night sky.
So what is the quote-unquote right kind of night for astronomy? Obviously, we want dark, but I'm assuming we also probably don't want any cloud cover.
Yeah, you want it to be reasonably clear. There can be all sorts of conditions. I was observing one night with a friend, and we're down in Nova Scotia, and the fog was rolling in. I actually packed up, but he kept observing, and I went over and said, hey, why are you still looking up? You can only see, the planet Jupiter or whatever was up. We could just barely see it through the fog. And he said it was incredibly steady. And then we looked, and it's the best view of Jupiter that I've ever had in my life. And sometimes you can take advantage of the different conditions, even if it's foggy or something like that, if you kind of know what to look for and you really start to learn the sky.
So are there any classes or courses that the Royal Astronomical Society provides to get people started?
Well, we don't do anything like that formally. So usually what happens is people like myself that are really keen and avid have taken an interest and done some training. We actually have somebody who can do training in our organization, and I've taken her training, and then I've started to teach my own courses, and that's sort of been a lesson in itself in doing that process. And really, my students have really taught me how to convey the messages properly.
So you may not have events or courses outright for teaching, but you can certainly hook people up with put them in the right direction.
Yeah, absolutely. Usually what people do is they usually come out and they have a lot of very specific questions to their own situation. Some people want to do astrophotography, and then we have people that are into that, so we line you up with those individuals. Or people like myself, I really don't do much astrophotography at all. I just like to look at the stars and usually just use binoculars or low-power telescopes. So I can take people out and really show them sort of the broad strokes and how the constellations kind of work and fit together and how the sky moves around us and why. And I think once people learn that, then they can kind of go off into their own direction.
So if there's only one takeaway that our listeners leave the show with, what would you like it to be?
People really should just try to go out and enjoy the night sky. Oftentimes people think it's going to be very, very difficult to learn, and it certainly is enjoyable and challenging, but you can learn the constellations. Really there's only about 24 constellations to learn and maybe a few dozen stars to actually really start knowing your way around the night sky. And I say, most people know the Big Dipper or another sort of star patterns, and you just start there. You start with what you know, and then you kind of build your way out looking at magazine star charts, or maybe when you come out to one of our meetings, you learn a little bit more, and you just build on that knowledge, because everybody knows something. Some people know the planets, some people know a couple of constellations, but you can even start with the moon and just use the moon to guide you, because you can figure out where that is in the night sky and then figure out what constellations it's passing through, and you can use that as a guide.
Chris, thanks so much for being here.
Yeah, thank you very much, Rochelle.
And if you'd like to learn more about Chris Beckett or the Royal Astronomical Society of Canada, you can visit our website at scienceforthepeople.ca, and we will have there all the links you need to get started. In the meantime, while you're clicking links, we would also appreciate it if you clicked on over to us on Facebook, Google+, and Twitter, where you can stay in touch with the entire Science for the People team. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.